All right, here's a video. We got a new topic here, calculus. And what is calculus? So we're going to try to cover this in a very short period of time. I'm hoping for like 20 to 30 minutes tops, but we'll see. What is calculus? So calculus is the mathematical study of change. It's very important. It's foundational to science, engineering, and technology. You've really got two main branches of calculus. You might have heard of this, you might have not. I don't know what your background is. This is for anyone, really. You have differential calculus, and that focuses on rates of change, things like slopes of curves. And then you have integral calculus, which is really focused on accumulation and area under curves. We talk about area. It's pretty easy. You look outside and you're looking at a piece of property, and if it's like shaped like a rectangle or a square, it's pretty easy to go length times width. You get the area really easy, square footage, square yards, whatever. But when you're talking about a misshapen curve, there's really not any good formula. You can't easily find the area of that. And so integral calculus is really good for helping us focus on finding the area under a curve. But we'll start out by talking about differential calculus a little bit. This is a branch of mathematics that studies the concept of the derivative, which we're not talking about investing here, but it measures how a quantity changes in response to changes in another. Um, Formally, it's defined as the limit of the average rate of change of a function as the interval approaches zero. And a concept, it's visually represented by the slope of a tangent line to a curve at some particular point. And so it might help just to see a diagram here. You've got a curve and a tangent line going through a point. So just want to cover some very basic concepts. I'm not assuming anybody's had any calculus. I had to take like 2 years of it back in college, a very long time ago. So integral calculus, that is the other branch. The concept of an integral. So the definition here, it's a measure of the total accumulation or the area under a curve. And this does have real life examples. I know a lot of people think, well, calculus is some abstract thing that people play with, but think about it. You've seen these problems like a train leaves Chicago going X miles an hour, 100 miles an hour, and it travels for 5 hours. How far does it travel? Well, you're making an assumption that the velocity, the speed of that train is not changing; it's staying constant. Well, we know that's not true typically, right? Speed can vary over time. And so a real life example would be trying to calculate the distance traveled when the speed of whatever it is you're looking at changes over time. Integration is really connected to area. There's this thing called Riemann sums, which it's named after I'm trying to remember his name now, but basically the concept here is that when you're looking at the area under a curve, you can sum a bunch of small rectangles under a curve and then approximate the area. It's easy to find the area of a rectangle. The problem is you're only going to be able to approximate that area, and you need more and more and more small rectangles in order to do that to get a more and more accurate value for the area under a curve. Now, integrals provide an exact value for that area under a curve as the number of rectangles you create approaches infinity. So it might be a little easier to show an example of that here. And actually, I want to turn on the pointer just in case I need to point at something. But here's an illustration of Riemann sums where you have f of x, a function here, and the function that they're using, I'll just read it here. It says, here is a graph illustrating the concept of Riemann sums. The blue curve, which is this blue curve here, represents the function f of x equals x squared. And these light blue or kind of cyan looking rectangles, they represent the approximation of the area under that curve using left endpoints for the Riemann sum. And by left endpoints, I mean you can see the left endpoint of each triangle is touching the curve. I mean, you can already see how inaccurate this is going to be because if I find the area of this rectangle, this one, and add them all up, I'm leaving out all these little triangular areas here. I'm not going to get a very good number, but you can imagine in your mind that I make a bunch of smaller ones over and over and over and over. Then this little space, these gaps get smaller and smaller, so the area I would be calculating gets more and more accurate. But you can't really physically draw an infinite number of these rectangles. Um, but what represents here is an approximation for the area under the curve. And the sum of those areas approximates what's known as a definite integral, and we'll talk more about that in a minute. But the sum of these areas approximates the definite integral over the interval 0 to 2. And you've got x going from 0 all the way out to 2, and f of x is the function value, which is x squared. So hopefully that diagram helps with that and understanding that. All right, so now we're going to look at the notation and the interpretation for integrals. The common notation here would be this symbol. Let me get my pointer going again, the laser pointer. I got this symbol, f of x dx. And the interpretation of this would be this is the total accumulation from one point to another. And we'll talk a little more about that. Here's an example. Integrate a simple function, and the example here is the integral x dx. So the integral of that is x squared over 2 plus c. And I know we're covering a whole lot in a short period of time, but just take my word for it that this would be the integration here of this function. And now we want to discuss a little bit about this odd thing called c, which is known as the constant of integration. What is that? The constant of integration is an arbitrary constant that's denoted by the letter c, and it's added onto the result of an indefinite integral. And we're going to talk more about that too. There's a lot of terms getting thrown out here. Remember, definite and indefinite integrals. This represents the fact that there are an infinitely many functions that might have the same derivative, differing only by a constant. And I know that might sound a little confusing, but I'm going to go through that a little bit here to try to clear it up. So why is that needed? Why is this constant c needed? Well, when you're taking the derivative of a function, any constant disappears because the derivative of a constant is 0. For example, if you look at this, d of dx, um, x squared plus 5, when you're taking the derivative, you end up with 2x. The constant disappears. This 5 disappears. If you're taking the derivative of a function x squared minus 3, then the derivative would be 2x. And so you can see here the derivative of x squared plus 5 is 2x. The derivative of x squared minus 3 is 2x. But now once you have the derivative and you go back to looking at the integral, well, I have no idea what the constant might be. It's either the minus 3 or the plus 5. These two functions have the same derivative. So what we do here to make up for that is we add this constant on. Both x squared and plus 5 and x squared minus 3 have the same derivative, which is 2x. So therefore, if you reverse that process through integration, we can't determine that exact constant. Once we're down to 2x and we're going the other way, I don't know if it's supposed to be the minus 3 or the plus 5. So we just tack on the c to account for all possible solutions. So in other words, when we're looking at this here, the integral of 2x dx is x squared plus c. So we add that constant. So hopefully that clears that up. And again, I know this is just a real big overview, and I'm not going to be able to go into a whole lot of details in a short video. This is just to kind of get things started. Now, where does this apply? The constant of integration is used only for indefinite integrals. And indefinite integrals are those that don't specify bounds. You don't see any numbers here as you do here. For example, this is an indefinite integral. The integral of x dx is x squared over 2 plus c. Now, for a definite integral, you do have limits of integration. You've got limits on that integral. The constant cancels out because it's evaluated as a difference. So in this case, if you've got this a definite integral here with the limits of integration of a and b, you're going to end up with f of b minus f of a. So this is really kind of a kind of a simplistic covering of it, but that's kind of where you're at with definite and indefinite integrals. Um, and here's an example where you want to find the indefinite integral of f of x equals 3x squared. So if we do the integration here, 3x squared, well, you raise x cubed, and then that's over 3. It doesn't show that here, so 3 divided by 3 is 1. So 3x squared dx integrates out to x to the cubed, but then you add the c on there, as we talked about before. We need to add that constant. Now, in this case, that constant really would be, I guess, 0 in this case, but there are other situations where that could change. So we still put the c on the end. The c represents all the possible vertical shifts of the function x cubed, each of which could have that same derivative of 3x squared, kind of what we talked about already. Um, so that constant of integration is really crucial in solving any real world problems out there, such as, differential equations, where C might represent like an initial condition or some starting value. All right, so here I want to go through just a scenario. Here's a kind of a real world example. And you've seen problems like this before, but most of the problems you see outside of calculus, the speed of a vehicle that you're looking at, you want to calculate how far it's traveled. You got the speed, velocity times time. Um, you got the speed here represented. Like you got a car moving along a straight road, and its speed v of t, which is in meters per second, it's given as a function of time in seconds. And in this case, the speed varies according to this equation. V of t equals 2t plus 3, where t, the time, is between 0 and 5 seconds. So we're looking to calculate the distance that this car has traveled from 0 to 5 seconds when the speed changes with this function. And again, like I said, a lot of times you've seen problems where the speed is fixed, the time is fixed, the car's going 50 miles an hour for 10 hours. Well, 50 times 10 is 500, so it's gone, if we're doing with miles, that would be 500 miles. 50 miles an hour times 10 hours, 500 miles. Really simple, but this is different. This is where the speed is actually changing according to a function. A little more difficult to figure. So, in order to set this problem up, we want to set it up using integral calculus. And so the first thing to do is write out the relationship between the speed and the distance. So in this case, this might look familiar. You've got distance would be the speed times the time, but in this case, we have an integral v of t dt. And to find that total distance, we got to calculate. We're gonna calculate using these limits 0 to 5, right? We said that we're looking from 0 to 5 seconds. And the function here for v of t, it's this 2t plus 3. That's our um, calculation of velocity or the speed here. Sorry, I keep bouncing around with that. But so you got 2t plus 3 dt to find the total distance. So in this case, we want to find the antiderivative, and we're going to explain that too. Um, the antiderivative of 2t plus 3, you can see we're working this out. It's 2t dt plus 3 dt, which then comes out to t squared. So if you integrate 2t, it becomes 2t squared And then you got 3, it becomes 3t. We're adding the integral constant on here. So we end up with t squared plus 3t plus c. All right, 2t squared plus 3t plus c. So I'm going to just make a little note in here before we go on to the solution, but an antiderivative is just the reverse of taking a derivative. It's a function whose derivative gives back the original function. I know that may sound kind of strange, but in other words, if f of x is the antiderivative of f of x, is capitalized f of x, is the antiderivative of this f of x, then um, the derivative of f of x equals f of x. So the process of finding an antiderivative is called integration. So it's kind of another way of just saying integration. And it's a fundamental concept in calculus. So some of the key features here of this antiderivative. So the general form, when you finding an antiderivative, there's always that constant of integration c that we've talked about, and it gets added to the result because the derivatives of constants are 0, as we discussed. So like with this one here, the integral x squared dx is x cubed over 3 plus c. And so we add that constant. And then since C, you have multiple antiderivatives because since C can be any constant, there's infinitely many antiderivatives for a function. For example, the antiderivatives of x squared include things like x cubed over 3 plus 1, x cubed over 3 minus 5, etc. Um, and then there's a connection here with definite integrals as well. While an antiderivative provides a general function, uh, definite integrals use the antiderivative to calculate the total change or area over a specific interval. And it's kind of what we're trying to do here with this example that we're going through with the car traveling. All right, so I do want to jump back here again to the example that we were working on. We said we want to evaluate the antiderivative from t equals 0 to t equals 5 for our example that we were working on. And we've already said that this 2t plus 3, that's our velocity, our speed, times dt, we're ending up here with t squared plus 3t, and we want to evaluate it over the limits 0 and 5. Well, that's fairly easy here. First of all, we put in the 5, we replace t with a 5, so it's 5 squared plus 3 times 5, and then we subtract, we put in 0 for t, here. So 0 squared, 0, plus 3 times 0 is 0. You're going to end up with 25 plus 15 minus 0 plus 0 is just subtracting 0. You're going to end up with 40 meters as the answer. So the car is going to travel a total distance of 40 meters during that 5-second interval. So hopefully that makes some sense. And again, I realize this is a very fast overview, and I'm not going into a whole lot of detail. But the one thing I wanted to try to tie together here is the connection between derivatives and integrals. We're talking about those two big branches of calculus. Derivatives of integrals recover the original function, and then definite integrals compute accumulation, like accumulation of area, using the antiderivative. So really, calculus is really about change. It's about differentiation, and it's about accumulation, which is what we see in integration. Those are the two big things. And the two of these are interconnected by what's known as the fundamental theorem of calculus. And so yeah, I'd say I encourage further exploration into this whole subject. I can't really possibly cover the whole thing in such a short video. But I will say that calculus has real world applications. I know that might not seem obvious to everyone, but I just showed one where, you've got a situation where the speed of a vehicle is changing, over time, and you want to calculate how far it's traveled. That's a pretty difficult thing to do without calculus. But it has real world applications in physics, economics, computer science, and many other fields that this does have a lot of use. And I want to thank everybody that stuck around through the video. And I want to say please like, share, subscribe, leave a comment. Let me know what kinds of things you would like to see in some future videos. And hope everyone has a great day.